Good morning, everybody. I'm pleased to be here. I'm here on behalf of the Mining and Geological Engineering Department. We are doing baby steps in the space, but starting on the moon, and we're developing some of the uh, uh, techniques or all the procedures that we may require for starting doing operations at the surface of the moon. So we're going to cover a little bit in a very brief mode, what we require for doing this from the miner's perspective. And we start with first knowing about the moon, the geology that is so complex and so rich on things to learn. We can start with the basics like basalt and silica, and then go into metals and other things, everything except copper. So perhaps Arizona will be the first provider of copper uh, supplies for the moon, like electric motors, wires, and other things that we might require. But the key or perhaps the precious element that we're looking after is water. And we are knowing more and more that there's evidence or presence of water, but we have to learn how to do it. Now, in accordance to what the Artemis project and NASA is looking after, they have prepared some competitions. We participated as the Wildcat Moon Miners, which is a team of undergrad and grad students, and some senior technical advisors from this university in two competitions called Break the Ice Lunar Challenge. We just arrived to the first stage, but for us it's a privilege, and we're proud of that. And this year we participated in Rascal for the first time, which is basically doing the supply chain management for a moon base that is already existing there, and we should be able to provide water, heat, food, and other supplies, including 3D printing pieces. There are some economics on mining that we've been researching, trying to see. I mean, it's very evident where is the wealth in going to the moon and extracting minerals for construction, for processing, and for creating things like electronics, solar panels, helium-3 fuel, and also fuel cells for hydrogen and the oxygen as precious as it is. So some economics talk about some of the demands, including also the construction of the Gateway, a space station that would be orbiting around the moon for the service of the travelers from the Earth to the moon. And also in the future, the creation of a launch pad for going to Mars, making the moon a sort of a gas station for the long journey. Well, we're starting knowing our neighborhood. Some of these things are kind of well known for the moon experts. And we have Shackleton, the southmost crater, which is not only huge, but interesting because it's the South Pole is at the rim of the Shackleton crater, so it's kind of easy to get there. However, we have other things for the purpose of this presentation, which has been presented also recently this year at the Society of Mining Engineering and Exploration conference. We selected one site, our interest, which is opposed to the South Pole, and also a place that could be reached of regolith or icy regolith because of its proximity to the South Pole, where is less presence of the sun, and that may guarantee that the ice that would be placed there from comets may not sublimate suddenly because of the exposure of the sun. So here we are using Moontrek, another free and open software by NASA that everybody could use at home. It's more or less like the Google Maps for the moon. And we found exactly the location where we want to go. There are several places around Shackleton that are called sites 001, 003, 4, and so on. We are looking for one at the east side, the northeast side of Shackleton, just because we'll see that it's looking at the line. I mean, we can see the Earth, and perhaps that is also good and rewarding for our benefit. But beyond that, we have other places that we will have spots, sorry, Spoodies, Marvin, we have Amundsen, and many other places, other craters that are also in the permanent shadow regions, means that they are completely dark almost the entire year. Means that if anything like ice is there, is kept there for millions of years and we can extract it. This is kind of the stratigraphic column of the icy regolith with progressing from the fine powdery material that we know from the Apollo missions and later other levels to some extent. This is by sound velocity tests and other things that were done by the low lunar reconnaissance orbiters. But the right one is the simplified that was used by NASA for the competition. So 3 classes of material that we could extract. And it would be more simplified for the purpose of this. The machine that we selected for that is one that already exists in the market. It's called a Razor. I guess it's done by Off-World, a company, but now they have associated with Redwire and are giving solutions for mining. It is our workhorse for the moon because they can go in both ways, and they have drums to shave the rather soft material, sort of a hard ice cream or something to excavate. Some of the characteristics, we have to deal with the distances that we can go, the timing for the life of the batteries, and the capabilities for doing that. And this is the principle of extraction that the machine can give us. This is the process that we presented as an experiment in association with Open Contour, a software company that does surface mining for the Earth. But they were so excited, and we worked together. We brought the contours from the moon, actual contours from the moon, and through QGIS, we're able to create a 3D shapefile and produce a mine plan. And the mine plan goes as follows. These are the digital elevation models and the actual contours, and then what we were able to do, the mine model itself. So we finished with, this is the plan. We tried to do the traditional Earth way, but it's not. We have to create a new one. And this one was called the Adams rib cage because it goes in different, either one and the other side. And those are the machines. We have several, including a charging station, a standby machine, and working for the first 3 months there, only the day part. So basically 14 days every month. But we were able to create a plan and have three types of material, 3 stockpiles that we could produce, and with the plan sequence of planning. And these are animations. Hopefully we can see some of them. If not, those are the, we have finished reclaiming the land because we want to preserve the beauty of our moon, and presenting that at least, yeah, there are animations. You can see how it works week after week after week for the first 3 months on the surface of the moon. And we're planning to do that. This is a different view of this, and we can do more. We still need to work on this given the costs and the breakdowns that we may have, and create an actual mine plan for the moon. But this is the first collaboration that we have done, and perhaps we're proud to say the first mine plan for the moon. And these are the results of that experiment. It's a mere 121 tons of valuable material. So we have to do a little bit more, perhaps have 3, 4, or 10 of these mine plans to produce something at industrial scale for our needs, but it could start. And this is kind of my pipe dream of how will it look, a mine plan for this. It's still a mock-up, even though last year I did a kind of a prototype in Python, not hard to do, but we need more of the background. So that's part of our research extension that we would like to do. So some conclusions is that moon mining is feasible, and it will be part of what we can do as miners in association with the astronauts. So that's a thing that we can do, and also we can work more in the batteries and the cycles and all these things. Some of the reference that we have used, and I'm open for questions.
All right, thank you. We have a question?
Thanks, Walt. My water bill at home is measured in cubic feet, hundreds of cubic feet, and it varies between 5 and 100 depending on winter and summer. So what is your estimate how many of these hundreds of cubic feet of water you can get out of the moon?
I guess that we can have as much as, well, I'll call it now in kilograms for the moment, 10,000 kilograms of water in a year of working. Perhaps that's what it is expected, but we may need more equipment and more planning and be sure that we. Yes, I think that is the estimate. Correct, but at least it's precious water. We can use it to some extent and start creating modestly our first fuel cells and using and reusing that water for human consumption and also for some of the processes we're going to do. It's still kind of modest. Perhaps there will be more abundance of things like basalt or silica or other materials. And some people may say the richest thing to get is the water, but regardless of that, is still one of the precious thing, even if it's in modest amounts. Perhaps we can find more and find other ways to process it in a more industrial scale. Thank you very much.